Chemistry for dummies like you. Today's topic is, drumroll please, periodic trend. So you can basically say this is a trendy video. You've probably scoured the internet not being able to understand anything, and you've been complaining to your mom about how you don't understand this and that you hate everything. Worry not, my friend. I am here. Your prayers have been answered. Come here, my child. My name is Professor P. P. Less. And I'm here to help you understand chemistry. So let's start with today's topic, which is atomic and ionic radii. Radius, if you want to say so. So let's start with some explanations, basically prerequisites to understand what we're going to talk about today. Our first topic is going to be shielding effect. Shielding effect can be defined as a reduction in the effective nuclear charge on the electron cloud due to a difference in attraction forces of the electrons on the nucleus. It is also referred to as screening effect or atomic shielding. Anyone works. A diagram to explain. The red are the shielding electrons, which are reducing the effective nuclear charge in green through to the valence electrons in blue. Another really important term is effective nuclear charge. What is effective nuclear charge? The nucleus of an atom contains positively charged electrons called protons, and electrons are attracted to the nucleus as they're negatively charged. However, negatively charged electrons around the nucleus are organized into layers called orbitals, which repel against each other and negate some of the positive charge of the nucleus. This results in a varying attraction of the nucleus on the electrons surrounding the nucleus, which is also known as the nuclear charge. The presence of electrons on the inner shells of an atom shield the outermost electrons from feeling the full positive charge. Because of the varying charge on the electrons in different orbitals, we typically refer to that as effective nuclear charge, which is the effect of the nucleus experienced by the outermost electrons of an atom, taking into account the shielding effect of the inner electrons. Core electrons, if you want to say so. Here's a diagram to explain how it works. I've shown the shielding electrons in orange, which are 1 and 2 for oxygen, and then we take the electrons and we subtract the both, and we get 6 as the effective nuclear charge. The same with fluorine. There's 2 electrons shielding, and you take the electrons and you subtract both, and you get 7 as the effective nuclear charge. Another really important topic is cations and anions. And ions are basically charged species, and they can either be cations, which are positively charged and which have more protons than electrons shown on the left, and anions are negatively charged because they have more electrons than protons shown on the right. Let's start. That was a lot. Let's start with the actual good stuff though. So, atomic radii, or radius if you want to say so, this is the distance from the nucleus of an atom to the outermost orbital of its electron. If you're a really complicated person, you can look to the right, but the left is basically a really simplified version of what it looks like. And if you're like me, your teacher handed you this thing, but you're really confused and there's just a bunch of circles, orange, green, red, yellow, you don't understand what's going on. So let's break it down further to understand what's going on. Let's look at the trends for atomic radius. So from across a period from left to right, the atomic radii increases, and down a group from top to bottom, the atomic radii increases. Why is this? So from right to left, the atomic radii increases because of effective nuclear charge. This is because the increasing effective nuclear charge, Ze, going from left to right across the periodic table, it pulls the valence electrons on the outer shell closer to the nucleus, reducing the atomic radius. As you can see here, I got the effective nuclear charge for nitrogen and oxygen, and we can see the 2 shielding electrons in purple. And we can see that both of them only have 2 electrons shielding them, but oxygen has 8 protons, so it pulls in the valence electrons more since there's more of a positive pull. Therefore, that results in a smaller atomic radius, as also shown on the chart on the top right corner. You can see the numbers and kind of tell the atomic radius, so yeah. And from top to bottom, the ionic radii increases. This is because in each new period, the outer shell of the electrons create a new energy level, so they're located further away from the nucleus. This has a greater effect than the increasing nuclear charge Z because of the shielding by the core electrons. As you can see, I've taken the effective nuclear charge of both of them again, but magnesium is further. As you can see, there's two shells for orbitals between the nucleus and the valence electron for magnesium. Therefore, the pull is weaker and it just stays expanded rather than pulling and contracting like beryllium, where it's really the valence electrons are really close to the protons. Therefore, this results in magnesium being bigger than beryllium, as seen on the chart again in the middle. Oh, woof, that was a lot. I know. We're almost done. Hang in there. Last topic. Okay, so let's talk about ionic radii, radius again if you want to say so. It is the distance from the nucleus of an ion up to which it has an influence on the electron cloud. Again, if you're a complicated person, the diagram on the right also shows it, but the diagram on the left is a really simplified version of what it looks like. So, some trends in ionic radii. The radii of cations are usually smaller than that of their parent atoms, and the radii of anions are usually larger than that of their parent atoms. You want to hear a joke real quick? An anion and a cation were walking down an alleyway, and the cation said, "Oh, whoa, I think I've lost an electron." And the anion replies, "Are you sure?" To which the cation replies, "Yes, I'm positive." Get it? Because I lost an electron. Anyways, that could help you keep it in mind. So, why is this? Tell me why. Ain't nothing but a heart. Okay, so why are cations smaller? Cations are smaller because there are more protons in the nucleus, therefore a stronger attraction. Here I've picked the handy dandy oxygen. On the right is a normal oxygen atom. On the left is an oxygen atom with a 2+ charge. As we can see, it has lost 2 electrons, but both of them have the same number of protons in the middle, and both of them have 2 electrons shielding. But because it has more protons, and less electrons, it pulls the valence electrons in much easier, therefore making it smaller. Why are anions larger? This is because of the extra electron in the anion results in a greater repulsion between the valence electrons. As you can see, I've picked carbon for this example, and we have a normal carbon atom on the left, and we have carbon with a 4- charge on the right. Over here, you can see that carbon has 4 more atoms. Therefore, we can assume it's going to be larger because electrons don't really like each other. They kind of want to repel and they want to spread out, right? So, as you see, the first circle is the normal carbon atom, and they're just sitting on their orbit. They're not repelling against each other, which is hence the normal size. The second circle, all of them are really spread out because they don't want to stay together. Therefore, they stretch the orbital, making the whole atomic or ionic radii larger. That's why anions are larger than their parent atoms. As we can see here, that's the example with all the other, that's same thing with all the other ones like nitrogen, oxygen, fluorine. I just wrote a BB to make you understand that it's bigger. It really is. Woof, we're finally done and I'm here. Okay, 60-second summary time. Let's see if we can do it. Atomic radii increases from right to left. It increases from top to bottom. Cations are smaller, anions are bigger. Things to keep in mind: effective nuclear charge, orbitals, energy levels, and electron repulsion. Really simple and easy. That was a good time. Until next time, bye bye dummies.